We've discussed continuous random variables before. Measurements such as heights, weights, blood pressure readings, blood glucose levels, all these kind of measurements form what is called a normal distribution. So if we make a histogram of such measurements, then the shape of the distribution that comes out from the histogram is a bell-shaped distribution. That is called a normal distribution, or this is also called a normal curve. There are two parameters that completely define a normal distribution, and the two parameters are mu, which is the mean, and sigma, which is the standard deviation. So n is for a normal distribution. N mu sigma would mean that the first number is the mean and the second number is the standard deviation. Now, if you remember from chapter 2, for a symmetrical distribution, the mean is always equal to the median. So the mean and the median are about the same value, or exactly the same value if it's perfectly symmetrical. Another thing about the bell-shaped distribution, that it's symmetric about the mean, which means the mean lies in the center of the distribution. If we draw a line right through the mean, a vertical line right through the mean, then one side of the curve is a mirror image of the other about the line, the red line that I've drawn through the mean. The total area under the curve is always 1 because the total probability of the sample space, all the probabilities, add up to 1. So if we look at the total area, the area under the curve is always equal to 1. We've seen examples of that before. So the total area under the curve is always equal to 1. The bell-shaped curve approaches the x-axis, gets really close to it, but never really intersects with the x-axis. So this is called the tail of the normal distribution. It just gets closer and closer to the x-axis, but never ever intersects with the x-axis. Another important property of the curve is this. When we look at one standard deviation to the right of the mean and one standard deviation to the left of the mean, let's observe the curve in that region. So we're looking at the graph, which is the bell-shaped distribution within one standard deviation of the mean, which means one standard deviation to the left of the mean and one standard deviation to the right of the mean. Notice that the graph is like this. It curves downwards, so it's called a concave down function in that interval from negative 1 standard deviation to positive 1 standard deviation. So we're looking at the graph in this range of values. Now, exactly at that point, which is 1 standard deviation from the mean in both directions of or on both sides of mu, which is the center, that is the mean, the curve flips and curves upwards. It's like a cup from that point on. So if you look at this, it's like a cup. So this is the point exactly, 1 standard deviation from to the right of the mean. The curve flips from a downward shape to an upward shape. And same thing on the left, 1 standard deviation to the left of the mean. Up to this point the curve was downwards, and now suddenly it flips and it goes upwards. So that is an important point. So if we know the mean, which is the mu, and sigma, which is the standard deviation of the normal distribution, then we should be able to sketch the entire graph, which is the normal distribution. So quickly reviewing the properties of the normal distribution or the bell-shaped graph, we have mu, the mean, sitting in the center of the distribution. If we draw a line right through mu, then one side of the graph is the mirror image of the other. So that's called the line of symmetry. The next important point is that the mean is equal to the median, because it's a symmetric distribution, and for any symmetric distribution the mean has to equal the median. Just like all distributions of continuous random variables, the total area under the curve is equal to 1. And we care about the areas under the curve because the areas under the curve give us probabilities. Another important property of the bell-shaped distribution is the curve is shaped downwards within one standard deviation of the mean, which means from negative sigma to positive sigma, the graph is like it's curved downwards, exactly one standard deviation away from the mean. To the right of the mean and to the left of the mean, the curve flips and curves upwards. The graph gets closer and closer to the x-axis but never intersects with the x-axis. So these are some of the important properties of the normal distribution. So let's quickly answer a few questions from the discussion we had on the previous slide. What are the parameters needed to graph a normal distribution? The parameters that we need to graph the normal distribution or completely define the normal distribution are just two numbers: the mean and the standard deviation. So it's mu, remember the letters mu, and sigma. The line of symmetry of the graph is the line passing through the center, which is the mean. It's mu, not sigma. So the line passing through the center is the line of symmetry. The parameter, which is the standard deviation, determines how spread out the data are. So for example, if the data are not very spread out, then the normal distribution looks narrow and tall, the graph looks tall. If it's very spread out, then the normal distribution looks broad and flat. They're all normal distributions, except that here the sigma is way less than the sigma here. Now in the given graph, can we identify the mean and the standard deviation? That's the question. So the mean, if it's a bell-shaped distribution, is always the center of the distribution. In this case, the mean is equal to 10. So that's pretty easy to identify. We could say it's roughly 10. Now the next thing is approximately determine the standard deviation. So the standard deviation can be determined by finding out where exactly the curve switches from being downward, graph that's going downwards, to a graph that's going upwards. So roughly we could say that the flip happens about here. So let's look at this. Between these two, if you notice, the graph is shaped downwards, so it's a concave down function, and exactly at that point the graph flips and becomes a concave up function. So we could say that's happening 2 units away from the center, which is the mean. So 2 is the sigma. So 2 units away from the center on either side of mu, which is the center, you'll notice that the curve flips from downward to upward. So that's how we determine, by looking at the graph, what the mean is and what the standard deviation is. So next the question says, sketch the graph that has the following conditions: curves with the same mean and different standard deviations. So the mean is always the center of the distribution. If you want the means to be the same, we need to make sure that all the various normal distributions that we sketch, all of them have a line of symmetry that passes through the center, the same center. It could be anything, and it could be on any part of the x-axis, but it would have to be the same. So they would all have to have the same center. So that's the condition if all the graphs must have the same mean. Now if we want the standard deviations to be different, standard deviation is sigma. Standard deviation tells us how spread out the data are. If we want the graph to be very spread out, then the sigma has to be sigma, or the standard deviation has to be large. If we want the graph to be tall and thin, if we want the normal distribution to be tall and thin, then we would like the sigma to be way less. So look at the three graphs that have been sketched here. They all have the same center. So they have the same mean, which let's just call it mu. Notice that we've made all the standard deviations different, and how does that show in the graph? Notice that they're all the spread of the graphs is different. The green graph seems to be the most spread out. Look at the green one, the most spread out of all the three. The tallest and least spread out is this brown graph. So that would be the least sigma. So sigma 1 is the smallest standard deviation. So it's less than sigma 2, which is the blue graph, and sigma 3, which is the greatest spread. So that sigma 3 would be the largest of the three numbers. So sigma 1 is the smallest and sigma 3 is the largest. Sigma 2, which is the standard deviation of the blue graph, sits between the two numbers. Here we are looking at an example where we have three normal distributions. Notice that the centers of the distributions are all different. So we have mu equals 0 for the first one, mu equals 2 for the second, and mu equals 1 for the second, and mu equals 2 for the third. So the green graph has mu which is equal to 2, the blue graph has mu which is equal to 1, and the black graph has mu equals 0. So they're all different means, but the standard deviation is the same. And how does that show in the graph? The spread of the graphs is all the same. So do you notice that they're basically the same graph except centering at different points, that is at 0, 1, and 2. Now let's look at the next example. So we have three graphs here. One is a green one is a red, and one is a black. They're all normal distributions. The question says which normal curve has the greatest mean. The mean always sits in the center of the distribution. So let's look at the mean of the green graph is here. The mean of the red graph, so this is the green mean, mu g let's call it. This is the mu of the red graph, and this is the mu of the black graph. So there are three centers, and these are the means. So notice that the mean that is rightmost would be the largest or the greatest mean. The mean of the black graph is to the rightmost of the three numbers, so that would be the greatest mean. Which normal curve has the greatest standard deviation? Standard deviation gives us the shows us the spread of the data, how spread out the data are. So if we want the greatest standard deviation, we'll have to look for the graph that looks the broadest and most spread out. So notice that the black graph out of the three is the most spread out of the three graphs. So that would be the graph with the largest standard deviation.